Okay, well, welcome everybody. We are going to be finishing up tonight section 1.3 about complex numbers, and then we will do sections 1.4 and hopefully all of 1.5. We'll see if we're able to get through all those, and that'll get us through quadratics, and that's as far as we're gonna maybe go tonight. So to begin with tonight, I've got a homework question that comes, and it's about complex numbers, and it's actually right where we left off on Wednesday night. So it'll be a good reminder of some of those concepts there. So we're looking at 1.3, number 20, and the directions are to divide two complex numbers. And it says, simplify your answer, use integers or fractions for any numbers in the expression. Type your answer in the form a plus bi. So this part right here, we'll have to make sure our answer is in the proper form. And it might be a little bit different than what we maybe would think is the final form. So we're starting with a plus 8 plus 3i over 5 plus 4i. And in order to divide two complex numbers, really we're going to try to make it so that the denominator is not a complex number anymore, so that it does not have an imaginary part. And we said the strategy for doing that is to multiply the top and bottom of the fraction by what's called the complex conjugate. Complex conjugate is 5 plus 4i, but instead of a plus, a minus. So we're multiplying top and bottom by 5 minus 4i. That numerator, we're going to have to FOIL. And so we'll do first times first, get 40. Outsides, we get negative 32i. Inside, we get plus 15i. Last times last, we get negative 12i squared. I times I being I squared, and we'll look more closely at the I squared on the next step. Let's go denominator. First times first, 25. Outside is minus 20i. Inside is plus 20i. And last times last is minus 16i squared. All right, a couple things to notice right off the bat. Minus 20i and plus 20i cancel each other out. Next things to notice. 32i and 15i are like terms, but they don't cancel out. One's negative, one's positive, so simplify that to 40, and then minus 17i. And negative 12i squared. Here's where we're going to deal with the I squared. Remember, I is this number that we've defined to be the square root of negative 1. And if I square I get plain old negative 1. So 12 times negative 1, negative 12 times negative 1 becomes plus 12 at the end here. So this is where FOILing complex numbers is a little bit different than FOILing just plain old polynomials. Denominator, we had 25, our i's canceled out, and again, negative 16 times a negative 1 for that I squared becomes plus 16. And so now I've got some more like terms to put together in the numerator, 40 and 12. So that's 52 minus 17i in the numerator. More like terms, 25 plus 16, and that would be 41, I believe. So on a test, if you can get this far, you've done great. That's a perfectly acceptable answer to me. If you do this division on a calculator, it's pretty likely that your calculator would show you an answer that looks kind of like this. However, the computer wants this in a little bit more specific kind of a form. So what they want you to do on the computer is separate the real part from the imaginary part. So we need to write 52 over 41 separately. And then, since it's minus, I'll put minus. 17i over 41. Also separately. So now we have separated out the real part and the imaginary part. And the computer should like that answer. Yep. Yeah, this is fine for me. Well, only if the fraction can be reached. Yeah, and most of the time I'm going to make it so it cannot be. I think if you've gotten that far, you've done all right. So even if it can be reduced on a test, I'll accept it not reduced in these imaginary complex numbers. Good question, though. Let's see, anything else about division of these things? And we also got to see multiplication of complex numbers in the process there. Adjust this thing just a little bit. That's better. All right, let me save this and close it up. And we'll go back to our class notes from before. These are things we just reviewed. Definition of I, and realizing that I squared is -1. And remember we did addition, subtraction, and multiplying, and just saw an example of division with complex numbers. So what else is there left to talk about on complex numbers? We're going to talk about, first of all, I did say that complex numbers and imaginary numbers, they're not just some kind of a pie in the sky kind of thing like rainbows and unicorns, and they're just in our imagination, and yeah, great for people who have imagination and mathematicians who want to do complicated things. No, they're actually useful in real life. So, an application of complex numbers. So this is going to, again, show a division problem. It turns out in electrical engineering and designing electrical circuits, complex numbers turn out to be the best way to represent certain quantities. By using them, you can incorporate the direction of flow of the electricity through a circuit. But here's a typical kind of problem that you might be asked to do. We're trying to calculate the impedance in a circuit when we're given the voltage and the current. So we're going to take voltage, 45 plus 88I, divide by current, which is 7 plus 4I, and that result will tell us the impedance on that particular circuit. All right, I'll go through this pretty quickly since we just did a division problem. We're going to multiply top and bottom by the complex conjugate. So we want to do 7 minus 4i are top and bottom. We'll have to FOIL on the top. We'll also FOIL on the bottom, but in the bottom, our imaginary parts will cancel out. And after a good bit of simplifying, and I'll let you, if you want to verify this, you can try the problem yourself and see if this is what you come out to. 667 plus 436i, all divided by 65. So check by foiling the numerator, check by foiling the denominator. These are the results you should come out with. All right, this could also be separated out as about 10.3 plus 6.7 I. And that's doing both of these parts divided by 65. So if you go into any kind of electrical career, you'll probably wind up using complex numbers, doing arithmetic with complex numbers. All right, one last thing about complex numbers. We've already talked about I and I squared. Let's look a little bit further though. We know that I is defined as square root of negative 1. I squared turns out to be negative 1. But what is I cubed? I to the third power. Well, I to the third power could be split up as I squared times I. So negative 1 times I, or simply negative I. And remember, in our visual depiction of complex numbers, we had the complex number line going vertical to the real number line. So we had positive values of I and we had negative values of I to the fourth can actually be split up as I squared times I squared. That's negative 1 times negative 1. So it results in being 1. But we can continue on with these powers. I to the fifth power. That's like I to the fourth times I. So 1 times I to the fifth should line up with this value. It goes right back to the value of I to the sixth is like I squared times I to the fourth. So negative 1 times 1, oh, it's negative 1 again. I to the seventh is negative I. And I to the eighth is like I to the fourth times I to the fourth. 1 times 1 is just 1. So I to the eighth is back to a 1. So fifth, sixth, seventh, and eighth powers just repeated I, negative 1, negative I, and 1. And we could go further. I to the ninth, I to the 10th, I to the 11th, I to the 12th. They all just reduce back to I, negative 1, negative I, and 1. And in fact, any power of I will go back to one of those four values. I, negative 1, negative I, or 1. Now, if the order seems a little bit weird here, if you have trouble remembering this order, here's a quick way to remember the order. Go back here. So we start with the imaginary constant I, and start working your way around. I squared is negative 1. I cubed is negative I. I to the fourth power is 1. And then we start the cycle all over again. Here's I to the fifth, I to the sixth, I to the seventh, I to the eighth. 9th, 10th, 11th, 12th powers of I. 13, 14, 15, 16th powers of I. So every fourth power of I, you wind up back at 1, and then you continue and start the cycle all over again. So the circle goes in that direction. I, negative 1, negative I, and 1. So how can we remember these things? Well, I've got some technical jargon up here, but all these numbers, 4, 8, 12, 16, they're all what you call multiples of 4. If you divide them by 4, what's your remainder? 12 divided by 4, so it equals 3, but what's the remainder? There is no remainder, 0. Okay, so quick way of saying, if I divide by 4 and I have a remainder of 0, I say that's 0 mod 4. I divide any of these numbers, 5, 9, 13, divide those by 4, they don't go evenly. They have a remainder of 1. I'll say those are 1 mod 4. These ones that are even numbers, if I divide them by 4, they don't go evenly. They have a remainder of 2, so they're 2 mod 4. And these ones would be 3 mod 4. They have a remainder of 3. And any number that is 0 mod 4, imaginary number to the power of something that can evenly be divisible by 4, that's going to always equal 1. If it's an even number, but not divisible by 4, that's going to equal negative 1. Evenly divisible by 4, that just reduces down to 1. Power that is even but not divisible by 4, negative 1. The odd powers either equal I or negative I, depending on where in the cycle they are. So I have up here through the 16th power, but I could also ask, for instance, what is I to the 240th power? Okay, well, can I divide that power evenly by 4? I sure can. If I divide it by 4, don't get any remainder, that means that that is equal to 1. I to the 240th power is 1. I to the 377. Well, it's not an even number. So I know it's not going to be 1 or negative 1, but the question is it I or is it negative I? So we need to decide where in that cycle are we. So I want to find a number that's close to that is divisible by 4. So I would think of 376, which is divisible by 4. So 376 is at the bottom of the cycle. Go back up to the top. 377 is the next one. That must equal I. 399. Well, where is that in the cycle? It's almost at 400, which is divisible by 4. So almost up to 400, but take one step back. Well, one step before 1 was negative I. So we just have to decide where in each of these cycles we are, or where in the cycle of 4 is each of these powers of I. Here's one last one, I to the 230th. Well, it's an even number, but if you divide it by 4, it does not come out with no remainder. So that means that's like I squared, so it's negative 1. All powers of I can boil down to one of those 4 values, which is nice when you're multiplying complex numbers. If you're multiplying lots of complex numbers, you know that your polynomial or your answer that looks like a polynomial is never going to have any high powers of I. All the powers of I will either turn into imaginary I or negative I, or 1 or negative 1. And that is, that's it for complex numbers. So most of you, I believe, have, or hopefully have started the Math Lab section 1.3 by now. You now can finish that section. And we're going to go on to sections 4 and 5. And that's the new handout that I gave you. Did anybody miss getting the notes guide? Everybody got one? Looks like you did. Very good. All right, so the first thing I'm going to do is I'm going to have you guys work with a graphing calculator. Hopefully you brought a graphing calculator with you tonight. If not, I will demonstrate this in just a few minutes. But I want to give you a chance to try this skill a little bit yourself. We have some warm-up questions, and directly under those warm-up questions, you'll see these directions. for how to use your calculator to solve a quadratic equation. So there are 4 problems to practice on. I'll let you guys try them out. If you need my help or if you're stuck on something, let me know. I'll give you a few minutes to try this, and then we'll come back and check them over. All right, hopefully you've had a chance to try maybe 1 or 2 of these. Maybe some of you who are a little quicker have gotten through more. But let's go over these, and I'll show you some techniques for working on a graphing calculator to solve an equation. And we'll do this applied to quadratic equations, but do understand that these techniques can be used to solve other kinds of equations too. And we'll get into some other types later in this chapter. And this might be kind of a good fallback if you really can't solve an equation. This at least can give you an idea of where the solution might be. So here's our process. We go to the y equals, and here's where we want to put the equation in. I'm going to put in x squared plus 5x minus 14. And hit graph. So if your graph does not look like this, it may be because you have a different window. And depending on what else you've been doing with your calculator, your window might be different than this. A good way to get back to what we call a standard window is zoom 6. Zoom 6 is called a standard window. It goes -10 to 10 on the x-axis and -10 to +10 on the y-axis. So what we're looking for, what we want to key in on, is the places where this graph crosses the x-axis. Right? Where it crosses the y-axis is not really that important to us right now. In fact, I know it's going to cross at -14 because it's at x equals 0, and at 0, this quadratic, all that's left is a -14. But I'm not concerned with where it crosses the y-axis. I want to see where it crosses the x-axis. And I happen to see 2 places. Now, if you're looking at your graphing calculator and you think you know one of the answers, you can actually skip some of this stuff and find your answer a little bit quicker. And looking at this, I kind of am guessing that one of the answers is x equals 2. I can hit trace, and then I have this little spider that crawls along the graph here and kind of skips over the value 2. X equals 2 just gets skipped over. That's okay though, I can just type in the number 2, hit enter, and it'll jump right there. And it gives me a y value. It says, yes, the y value is equal to 0. So that confirms that one of my solutions is x equals 2. X equals 2 is one of the things that will make this quadratic equal 0. Now, if your guess is wrong, then you're going to have to resort to the technique that I have in the directions there, which is to say second trace, find a 0. Now we have to give it a left bound to the left of our 0, and we have to give it a right bound to the right of our 0. You can either use the spider to crawl along and go to the left and to the right, or you can also type in values for your left bound and right bound. So once you've got your left bound, right bound, hit enter, and the calculator will find the x value that gives you 0. All right, so we've got one solution found, x equals 2. Let's look for another solution. So we have another solution over to the left here. If you have a guess as to what it might be, maybe you can hit trace and put in your guess and find out what it might be. If you're not sure what it might be, you're having a hard time counting the little dashes there, just go second trace, find a 0. It asks for a left bound. Well, rather than travel all the way back there, maybe I'll just say, okay, I know it's before I get to -9, so that's a good left bound. And it's got to be after, say, -4. So that would be a good right bound. And As long as those lines enclose that place where the 0 is, you're fine. Hit enter one more time, and it will find that 0. So -7 is our other solution to this quadratic. All right, so we found two solutions, -7 and +2. And in the computer, I think you'll have to separate your answers by a comma or something like that. -7 and 2. Let's go to the next one. I'll start speeding things up here. We'll go back to our y equals, put in a new equation. 2x squared plus x minus 15. And double check, make sure you came out of that power and the plus x minus 15 isn't up there with the 2. And if it's entered in there correctly, you hit graph, and hopefully we'll see the two solutions. Well, there's one, there's two. So looking at them a little bit bigger, it looks to me like one of those answers might be -3. Let's just check and see. Trace, and I could use my arrows, or I could just type in the number -3. And yeah, it does make y equal 0, so I guessed well. That was a good guess for that solution. The next one's right between 2 and 3. If I had to guess, I'd say 2.5. Turns out that guess is correct, but just to see the process again. Second, trace, find a 0, give it a left bound, give it a right bound, hit enter one more time. 2.5 is our other solution. So both these quadratics turned out had two solutions. That is typical of a quadratic. We'll talk more about how many solutions to expect later on, but we got x equals -3 and 2.5. All right, let's move on to the third question. 3/5, oh boy. That one's going to be a little more challenging to put in our calculator, but let's see how we can do it. Let me give you two options for fractions. Parentheses 3 divided by 5. There's a fraction. 3/5, close that parentheses, x squared. Minus, if you prefer, you can use the fraction button on your calculator, alpha y equals, and do the fraction 8 in the numerator, 3 in the denominator. It's bigger. So 8 over 3, and then x. So if you want your equation to look just like it does on paper, you can. Do that, and plus 1.89. And let's take a look at the graph. Thinking about it. Oh, there's one place it crosses, the second place. Hey, it looks like one of my solutions might be +1. So if I have a guess, maybe I'll do that. Hit trace and type in +1. Oh, it turns out that is not a solution. So don't accept close to 0 like that. It's got to be a whole lot closer to 0 than that to be a 0 of the function. So 1 is not a correct answer. I guess I'm just going to have to let the calculator do its thing. Second, trace, find a 0. Left bound, right bound. Well, I know it's between, say, 0 and 2. Right bound 2. There we go. And in between those, the actual 0 happens at 0.8849 or 0.885. How much do we need to round this? Depends. The computer will tell you a certain number of decimal places to round to. I like to see 3 places after a decimal. But if you're showing your work and explaining your work, then as long as it's correctly rounded. And don't say it's 1, right? Don't round it so much that it loses all of its accuracy. But I'm flexible on the rounding. All right, so there's one of our solutions. There's another one over here to the right. Looks like at about 3.5, but I doubt it's actually 3.5. Let's try and find out. Second trace, find a 0. I need a left bound and a right bound. And remember, you can make these close, you can make them far apart. Just don't make your left bound and right bound so that it contains 2 separate answers. Got to surround just a single answer. Let the calculator narrow in on that, and it turns out it's 3.559. So not quite 3.5, just a little bit more than 3.5. So our solutions, x is about, I'm making squiggles because that's approximately 0.885 and 3.559. And finally, x squared minus 2x plus 7. Let's go through our whole process again. We're going to put it in the y equals, and we're going to take a look at the graph. I'll clear that. X squared minus 2x plus 7 graph. Remember, I'm looking for where this crosses the x-axis. Oh, it just turned around before it even got down there. Well, quadratics, once they turn around, they're never coming back down. This shape, called a parabola, always starts high and ends high, or starts low and ends low, if they're upside down, but never coming back down there, so it's never going to cross the x-axis. So there is no solution for this one, because there are no x-intercepts. Well, let me amend that. There is no real solution. No real solution. So we're going to see this is the type of quadratic that has complex solutions. Complex solutions are not on the number line, so I wouldn't expect to find them on the x-axis. We're going to need a better technique for solving that type of equation. And if we want exact answers, we're going to need a better technique for solving that third one. Because all I could do, the best I could do here is put approximate answers. So let's talk about some more methods of solving. That's all we're going to do for graphing calculators today. So if you got that, then good. You've got a new skill that you've learned through your calculator. Practice it a little bit, and you'll get the hang of it. Just remember how to get it started. That's kind of the important process. The calculator will ask you questions along the way, but you just have to remember how to start the process. So, quadratic equations. Hunting zeros is what I call it. So what is a quadratic? We just saw 3 examples of quadratic equations, but a quadratic equation is any equation equivalent to ax squared plus bx plus c equals 0. You must have an x squared term to be quadratic. You don't have to have a linear term. So b could be 0. Could be like 0x and you don't even see an x term. C could also be 0. You might not even see a constant term there. But you must have the squared term. So a cannot be 0. Ax squared plus bx plus c. We will not always see quadratics given in this form, but with enough manipulation, a little bit of algebra, we can get them into this form. Once they are in this form, then we have some different choices for how to solve them. Here are the methods. Graphing to find zeros. We just did that. And it's good to a point. You can't always get the exact answers that you need when you're using the graphing method. If you need exact answers, here are some of the methods that we're going to talk about tonight. Factoring. For factoring, you better have that thing already equal to 0, or you shouldn't start factoring yet. The square root method, which leads to completing the square. The square root method, I'll tell you, is best when there is no term that's bx. So if you don't have a number times x, you only have a squared term and a constant term, the square root method is a good method to use. Completing the square, that's a little bit more complicated when you do have that dx term. We'll look at it a little bit, but really what we're looking for is to see the connection between completing the square and our other method of solving quadratics, which is quadratic formula. Quadratic formula is another one where we need to have the equation written in this form, everything on one side of the equal sign equal to 0. Because we'll need to identify that A, B, and C to use the quadratic formula. So let's see what some of these methods look like. We'll start with factoring. So factoring, we're going to look at parentheses, parentheses, that kind of factoring, because there's no common factor. And we did a lot of this in chapter R, so hopefully it's still in your memory here. I need to get first times first equal x. X times x. I have to say most people on the test were pretty good at this basic factoring. 14, right? I skip to the end. I need numbers that multiply to get 14. I'm going to choose 7 times 2. Because 7 and 2 are 5 apart, and that gets me the number in the middle if I use a plus 7 and a minus 2. Now this will FOIL back to x squared plus 5x minus 14. Now the factors, each factor will tell me one of the solutions. But the solutions are not 7 and negative 2, because really we're trying to make each factor equal to 0. 7 plus 7 doesn't equal 0. But if x equals a negative 7, negative 7 plus 7, that is 0. And 0 times whatever is going to equal 0. Likewise, for the second factor, x equals 2 is the solution, because 2 minus 2 is 0. Notice that each of my solutions has the opposite sign from the factor it came from. There was a plus in one factor, solution is negative. There was a minus in the other factor, solution is positive. And negative 7 and positive 2, that agrees. We go back to our first problem, because it's the same problem. So we should get the same answers no matter what method we use. Got the same answers when we graph. Now we get the same answers when we factor. Next one, let's factor. Parentheses, parentheses, because I cannot take out any common factor. Can't take out 2, I can't take out 5 or 3 or anything like that. Just unfoil. We're going to start with 2x times x. And let's see, there's not too many choices here. Let me go with a 5 times 3. So I think I made a lucky guess here. Got it maybe on the first try. Because the outsides would be 6x. The insides would be 5x. And I can make that equal positive x. If it's a positive 6x and a minus 5x. So outsides, that's the one I want to come out positive. And insides, that's the one I want to come out negative. Well, x plus 3 is just like these ones over here. Easy solution, just change the sign. X equals negative 3 is the solution for that factor. Now, if you run into one that's a little more complicated, the answer here is not positive 5. We need to solve a little mini equation. 2x minus 5 equals 0. Let's add 5 to both sides and divide both sides by 2. So x is equal to 5 halves, and also known as 2.5. And that one also agrees with the answer we got when we graphed. That was the second one we graphed. Our answers were 2.5 and negative 3. There they are, 2.5 and negative 3. So factoring gives us a solution without having to mess with the technology. If you don't have the technology with you, or you don't want to get it out and waste the time with putting it in the y equals and all that business, factoring is your method. All right, we got 6a squared plus 23a equals 4. Oh, look, a squared and a, maybe I can factor out an a? Or should I try to unfoil? Wait, there's only two things here. Wait, don't start factoring yet. Because what did we say? Make it equal to 0. Yep, so first thing we got to do here, and I actually already have these ones solved out here. First step here would be subtract 4 from both sides. Now I have it in a form that can be factored. This doesn't look like the easiest thing in the world to factor, but I've already done it, so we'll jump ahead right to the factors of 6a squared plus 23a minus 4. The factors are 6a and a, 1 and 4, with a minus in front of the 1 and a plus in front of the 4. We'll save you guys some time with guessing and checking. And our solutions then are a equals -4, that's the easy one. And for 6a minus 1, if you need to write out a little mini equation like we did up here and solve it, that's fine. Some people can look at it and think in their head, what are the steps I'm going to do to solve it? I'm going to add 1, I'm going to divide by 6. 1/6 is going to be the solution. And there we've got our two solutions for that quadratic. All right, so let's talk about the one time when you don't have to have it equal to 0. And that's with the square root method. Now, when I said the square root method works best when there is not an x term, this is what I meant. I have x squared equal to 26. I have an x squared term, I have a constant term of 26, but I don't have any 3x or 5x or 7x or something like that in the problem. And here's what the square root method does. We take the square root of the left side and the square root of the right side to undo the squaring. But we need to remember something key here. When we take the square root of 26, we want to get two answers. There should be two solutions for this quadratic. So we need a positive version of square root of 26 and a negative version of square root of 26. We can use the plus or minus symbol, plus or minus square root of 26. You'll have to check on the computer and see if the plus or minus symbol is there and available. If not, then usually you write it as two separate answers. Separately write square root of 26 and negative square root of 26. And with that, you're done. That's all there is to that kind of a problem. We don't need to figure out a decimal approximation for that. If we wanted a decimal approximation, we might as well solve it on a calculator. We want to keep our answer as exact as possible, square root of 26. Now, maybe you can simplify the square root. Again, the computer might be picky. They might want to simplify the square root. On a test, I'm not going to be that picky. If you can think of a way to simplify the square root, okay, but you don't have to on a test. Let's look at this. T squared minus 8 equals 5, but it doesn't look like this. I can make it look like that first one, though. Pretty simple. Just add 8 to both sides. Now it's just like the one we did before. Something squared equals a number. And we'll use the square root step. Remember to put plus or minus square root of 13. Two solutions. Positive version and a negative version. And what you would see if you graphed x squared minus 26, you would see a parabola that hits the graph in both of those places. One on the right side of the y equals 1 on the left side of the y equals. Or t squared minus 13. You graph it on a graphing calculator, you'll see it'll hit the x-axis twice. Once at positive square root of 13, once at negative square root of 13. All right, looking at the next one, z squared plus 11 equals negative 5. Well, it doesn't look quite like these, but it's kind of like that second one. I suppose I could subtract 11 from both sides, and that would have something squared equal to a number. Oh, but wait, it equals a negative number. Well, that's okay. Just the last section, we learned how to take the square root of a negative number. The square root of negative 16 involves the imaginary constant, I. Be sure again to put a plus version and a minus version. Positive 4i and negative 4i. Plus or minus 4i. All right, whoa, that last one doesn't look anything like the first one. Way more complicated than that. Quantity w minus h squared, but let's just follow what we've been doing so far. It worked before, maybe it'll still work. Let's subtract the 6 from both sides. So we can subtract 6 from both sides, leaves that quantity w minus h squared. On the other side, we have 7. Well, what was our next step in all the rest of these? It was to do the square root step, remembering a plus or minus. So we're going to do the square root step to both sides and put on the right side plus or minus square root of 7. Now, square root undoes the squaring. So now I don't have a quantity squared anymore. I just have w minus 8. You know, at this point, usually after the square root step, we were done. We're not quite done yet. One more step and we will be done. Add 8 to both sides. And traditionally, we'll put the rational number and then plus or minus the square root of the irrational number. 8 plus or minus the square root of 7. And that last problem there is pretty close to the technique called completing the square. Completing the square is a technique that allows you to use the square root method even when you have an x term. So let's see that on the next page. We're going to see how we can continue to use the square root method, although once you have an x term, the steps get pretty complicated. So let's take a look on the on this, and all right, so this one have, of course, the first step, which is the problem that we're going to solve. X squared minus 14x plus 3. And then I have a next step. As far as completing the square, this next step is the key one that you need to know. You're not going to have to do a completing the square problem in full on the test. But this next step is something that you're going to need for this technique. You're going to need it also in future chapters. So let's see what this next step is. This is why we call this thing completing the square. I want to complete x squared minus 14x plus something to make that factorable. I want to pick a number that will make that factorable, but not just factorable. I want it to be the best kind of factoring we could have. The best kind of factoring we could possibly do to that thing is if I could factor and both factors look exactly the same. I don't want to use like a plus 13 and a plus 1 or a minus 13 minus 1. I don't want to use a minus 10 and a minus 4. I want them to be different. I want the same thing in both of those factors. And here's how we're going to figure this out. So what is the same number plus itself that will equal negative 14? Yeah, negative 7 and negative 7. So I want my factors to be x minus 7, x minus 7. That tells me what that third number needs to be. What is 7 times 7? 49. That's what I'm going to fill in that blank with. And over here to the left, it says we're going to take b divided by 2 and square it. So take half of that middle number, which is 7, and square it. That's what number goes into the blank. Now, of course, that's just thrown this whole equation off balance. So we need to balance it back again and add 49 on the other side as well. So we just added something to the same thing to both sides of the equation. We're definitely allowed to do that. So I'll talk about finding that magic number. Okay, that very best number so that this can factor. And as I said, I want it to be able to factor as an x minus 7, x minus 7, which I could also write as quantity x minus 7 squared. And maybe now you see where we're going with this. We have something squared equals a number. So I can use the square root method from the last page. I'm going to take the square root of both sides. Remembering plus or minus the square root of 46. And one more step and x will be all by itself. Isolate that variable. Positive 7 plus or minus the square root of 14. Square root of 46. And there's our solution. So it's kind of a number of steps here. It's not just one quick calculation and you're done. We do a step, we do another step, we do another step. Finally, x is by itself. We're done. And really, none of these steps, I don't think, is just obvious intuition. Right? It's not like solving a linear equation where I know, well, I want to get rid of that number, I want to get rid of that number, I want to get rid of it until x is by itself. That's not how this works. So the first few times you do this, have your notes in front of you. Have these directions in front of you. You want to do completing the square. All right, let me show you how this gets even worse. And you do not need to write this one down because it's already in your notes, already fully worked out. So just follow me. I'm going to do this pretty quick and show you how complicated this can get if there's a number in front of the x squared besides 1. Right, 7x squared. This makes it way more complicated than just x squared. Well, first step is we're going to add 8x to both sides. And I'm going to subtract the 3 over to the other side. It's okay to have a constant over here when we're completing the square. We don't have to have it equal to 0. If you want, get everything equal to 0 and then subtract 3 from both sides. Our next step is where we're going to try to, wait a minute, I can't try to find the magic number because of this 7 yet. I need to divide everything in this equation by 7. Now it's going to work like on the last page. I just need to figure out what half of 8 sevenths is. Half of 8 sevenths is 4 sevenths, but then I got to square that. 4 sevenths squared is the magic number that's going to go in this blank. But I also have to add it over here, and over here I'll go ahead and square it. 16 and the denominator is 49. So by picking exactly the correct number over here, that means I can factor that left-hand side in the best way possible. X plus 4 sevenths, x plus 4 sevenths. Same thing twice. But oh, over on the right-hand side, I've got fractions that don't even have common denominators. All right, well, if you find common denominators, if you add them up, you get negative 5 over 49. And finally, we're going to do our square root step. Remembering plus or minus, oh, it's a negative that I'm taking the square root of, so this is imaginary, and x isn't by itself yet, so we've got to subtract 4 sevenths. Ooh, what a mess. So, sure would be nice if there was just some kind of machine that would do that for us. Just do all those steps for us. And there is. Let me show you how that works. And this is where it is on this page. All you got to do is write down punchline at the very end. So instead of doing this with the numbers 7, 8, and 3, I'm just going to do it with an A, a B, and a C, but using the same techniques here. So we'll go quick, but see if you can keep up. I got ax squared plus bx plus c. First thing I did was I subtracted the c from both sides, and then I did have to divide everything by a. So I get to that step. Then I have to find my magic number that has to go here, the best number to put here so that it can factor, and it's going to be half of b over a, or 1/2 times b over a, b over 2a, and then I got to square it. Now remember when I wrote it on this side, I actually did square those. So I'd get a b squared and a 4a squared. Then I factored the left side and I somehow found common denominators on the right side and put them together. Well, there's what it looks like with a's and b's. Now I do the square root step. And while it was kind of tough to square root the numerator, at least I can do the square root of 4a squared, because that's pretty easy, that's 2a. But I can't really simplify the square root on top very much. Squaring will undo, or square root will undo the squaring. And as a final step, I isolated the x. Got to this. Opposite of b over 2a, plus or minus the square root of b squared minus 4ac over 2a. And those of you who remember your some basic algebra will recognize that formula as a form of the quadratic formula. So the quadratic formula really is just an automated way of completing the square. Now you do have to remember the formula. It's got some details in it, but the more you practice with the formula, the more you'll remember those details. Now a lot of times you'll see the quadratic formula written as a single fraction. Kind of like on the left side, I have it all over 7. And a lot of times you'll see the formula, the whole thing over 2a. That's okay. I prefer to keep it separate for a couple of reasons. Number one, I tend to make fewer errors that way. Errors typically come when we're trying to simplify these, and people will reduce that fraction. They'll reduce part of the answer with the 2a, but not the other part with the 2a. So we're going to try to avoid some mistakes when simplifying. Also, we'll see that negative b over 2a has some meaning when we talk about quadratics as well. So it's nice to know what that is separately from the rest of the formula. All right, the quadratic formula. Opposite of b over 2a plus or minus the square root of b squared minus 4ac over 2a. Let's talk about how to use it. The first thing I do whenever I do the quadratic formula is I do b squared minus 4ac. Middle number squared minus 4 times the first number times the last number. Do that calculation, figure out what that number is. It'll make the quadratic formula, the entire quadratic formula, so much easier to plug numbers into. That expression, b squared minus 4ac, actually has a name. It's called the discriminant. And being the discriminant, it will be able to tell us what kind of answers we're going to get. If that discriminant equals 0, that means the part under the square root is 0. In fact, it means the whole left, right-hand side of that formula is 0. So really, I just get negative b over 2a plus 0 and negative b over 2a minus 0. I get the same answer twice. Same answer both times. Doesn't matter if I add or subtract 0, it's the same. So if that b squared minus 4ac equals 0, then you just saved yourself a whole lot of money. Just write negative b over 2a, you're done. Do the calculation with the numbers b and a. If the discriminant is greater than 0, meaning a positive number, then you are going to get one answer when you add and another answer when you subtract. They'll both be real answers. They'll be on the real number line, on the x-axis. Two unequal real roots, we say. if b squared minus 4ac comes out negative. Well, we all know what's going to happen when we try to take the square root of a negative number. We're going to get an imaginary. Our answer is going to involve I. So as soon as we know what b squared minus 4ac is, as soon as you calculated that number, you've got some idea of what your answers are going to be. Now, I did tell you that negative b over 2a is important in this formula also. And I like to keep it separate so that I can know what it's telling me about the graph. So each of those graphs that we drew is called a parabola. We saw those on the graphs at the beginning of class. It's a parabola, it's like a U shape, either right side up or upside down. Well, negative b over 2a tells you where the center line of that parabola is. So I'm going to demonstrate some of these by doing the discriminant calculation first, then putting the pieces into the formula. So do that b squared minus 4ac part first. And I think I left some blank spaces on the handout for you to maybe do one or two of these examples. You don't need to do every single one, but you can do as many as you feel like you need to. X squared plus 5x minus 14 equals 0. We're going to try to use the quadratic formula. First thing we've got to do is identify a, b, and c so we can use them in that formula. So look for the number in front of x squared, the number in front of x, and the number that's by itself. A, b, and c are just those numbers. So don't write that b equals 5x, just the 5. And a is not 1x squared, it's just the 1. So we just want numbers. A, b, and c are just numbers. Those are my three numbers. I'm going to do b squared minus 4ac. 5 squared minus 4 times 1 times negative 14. Use all three numbers in that calculation. 5 squared minus 4 times 1 times negative 14. Get out a calculator if you need to do that calculation that way. Comes out to 81. Now here's what makes doing the quadratic formula easy if you've done this first. I'm just going to set up an empty quadratic formula and let's see what we need to fill in. So there's empty quadratic formula, two fractions. That first fraction is going to have opposite of b over 2a. That's negative 5 over 2 times 1. There we go, negative 5 over 2. Now in the square root, do we need to do b squared minus 4ac? No, we've already done that. It's just a number. We're just going to put that 81 in the square root. And in the denominator, same denominator we already had, 2. And we filled in all we need to fill in the quadratic formula. If you do all that work ahead of time, then you don't have to write the quadratic formula 5 times while you simplify it. Right? A lot of people will do that and they'll make mistakes as they go because they got all this stuff under the square root and it gets all jumbled and it's too much to write, too much to keep track of. Do the calculation first, then you just got to fill in 4 numbers. You got your quadratic formula. Oh, this can simplify. Square root of 81 is a 9. So we'll get one answer when we add these. We'll get another answer when we subtract. When we add, we get 2, because it's 4 over 4. When we subtract, we get negative 7, because it's negative 14. Sorry, 4 over 2, this is negative 14 over 2. And this, once again, agrees with the very first problem we did when we graphed this. Saw the same solutions when we factored it. Saw the same solutions when we did the quadratic formula. Now, given a choice, I probably would not do the quadratic formula on this problem. It was a whole lot easier to do factoring, right? That was a whole lot fewer steps. So if you can factor, that's the preferred way to solve a quadratic. Don't just automatically jump to the quadratic formula. It's only when you can't factor. That's when you should probably jump to the quadratic formula. But the answer comes out the same either way. Here's a new one. 3x squared minus 18x plus 27. Let's see, I suppose I could factor out a 3 and then do some more factoring. And yeah, maybe I could factor it, but let's do the quadratic formula. A, B, and C. It's 3, negative 18, and 27. And you don't have to write these down every time. Most people are good enough that they can see what A, B, and C are without having to write them down separately. But do keep track of positive and negative signs. You don't want to have that B is 18. That negative needs to come with the 18. Let's do the calculation. B squared minus 4AC. Let's see. Lots of you have calculators out. I'm going to give you a second to do B squared minus 4AC. So get a calculator using those three numbers. Do B squared minus 4AC. And we'll see if we can head off a common mistake. All right, I'd be willing to bet that probably divided between two answers. All right, how many of you got the answer negative 648? All right, not bad. Okay, a few people got that. How many got the answer 0? All right, it's about even. Should we vote? That's how we settle things in mathematics, right? Majority rules. No, I don't think that's how it works. Now, it's not majority rules. One of those is right, one of them is wrong. Let's see which one is wrong. So check and see on your calculator if you started out by doing negative 18 squared, like that. Now, first of all, before we hit enter, what should a negative times a negative be? Positive. So negative 18 squared should be a positive number. Oh, my calculator is broken. Because they told me a negative number. No, my calculator is not broken. It did exactly what I told it to do. It followed the order of operations. It did 18 squared and then it multiplied times negative 1. Exponents come before multiply. If I meant negative 18 squared, what I should have put was parentheses negative 18 squared. 324. Should come out positive. Or if I don't want to mess with the negative, I'll just put in 18 squared, even though I know it's negative 18 squared, because I want that to come out positive. And then minus 4 times 3 times 27. So if you got the 0 the first time, good job. If you didn't get it the first time, that's a quick way to correct it. If you're going to square a number, just square the positive number. It's going to come out the same either way. Or, be careful about using parentheses. That's a whole lot more typing than just 18 squared. Correct answer for B squared minus 4AC should be 0. Well, that means when I actually fill out the pieces of the quadratic formula, I'll put a positive 18 over 2 times 3, or 18 over 6, and then square root of 0 over 2 times 3. And I can just ignore the whole part that's after the plus or minus because it's just going to be 0. So I only get one answer. I get 18 divided by 6, which is 3. And I get that same answer twice. One time when I add 0 and one time when I subtract 0. But it's the same answer. Visually, what you'll see on these kind is it's a parabola that comes down, touches the x-axis, and goes right back up. Never even cuts through. One solution. All right, one more example. X squared minus 12x equals negative 37. A is 1, B is negative 12. What is C? Think about what C is before you answer. Hopefully you didn't say negative 37, because we got to, first of all, make it equal to 0, right? Quadratic formula is one of those ones where you got to be hunting for zeros. And now we're ready to do A, B, and C. 1, negative 12, and 37. So what's B squared minus 4AC? Oh, negative 12 squared. I'm just going to do that part in my head. I know 12 squared is 144. So maybe I do that minus 4 times 1 times 37. I'm a little worried here. I think 4 times 37 might wind up being more than 144. So I might be subtracting a bigger number from a smaller number, and that's true, yeah, the difference there is negative 4. So B squared minus 4AC is negative 4. Right now, I know that both of my answers are going to be complex answers. They're going to have I in them, the imaginary constant. All right, but I'd rather do this calculation stuff outside of the square root than having to write the quadratic formula 5 times while I do all that simplifying. Now the quadratic formula, I just got to fill in 4 different places. Opposite of B, that'd be positive 12. Over 2A, that'd just be 2. Under the square root, that's where my calculation was for the negative 4, so I just put negative 4 under the square root, and also put it over 2. Hopefully this saves you some of the headaches that people go through doing the quadratic formula. You could keep writing these square roots, and it's a fraction, and do it this way, and there's a whole lot less simplifying at the very end. Now this square root of negative 4 is going to be 2i. So we'll have 12 over 2 plus or minus 2i over 2. And each of those can be reduced. 12 over 2 is 6. 2i over 2 is I. So we finally wind up with 6 plus or minus I. And let me talk about the one final common mistake that I see, which hopefully you avoid if you do it in this way. So here's what I'll see a lot of people will wind up doing. People who do the quadratic formula and put the whole thing over 2. They'll get 12 plus or minus 2i over 2, and they'll see, ooh, I see a 2 on the top and a 2 on the bottom, and they'll cancel those out. And they'll say, okay, the answer is 12 plus or minus I. Which is not correct. That's this kind of halfway reducing is a very common mistake people make. And I try to avoid that by just keeping it as 2 separate fractions. And then I'm not even tempted to do kind of this halfway reducing of a fraction. Maybe you guys can avoid that mistake too. All right. So that actually gets us to the end of section 1-4. And we'll continue on here with 1-5. I'm sorry we're not going to take a break tonight, but we'll just kind of try and push through here and finish this off as much as we possibly can here. So we're going to move to 1-5, which is equations and word problems and mathematical modeling that we need to solve using a quadratic equation this time. So all the ones in section 1-2, I think you used linear equations to solve your word problems. Now we're going to start using quadratic equations to solve our word problems. And some of them will be quadratic, not all of them will. Some of them will still be linear. All right, remember, common setups for word problems. Blank plus blank equals total, or blank equals blank. Hopefully, if you've done section 1, 2, you saw that almost every single problem boils down to this. Blank plus blank equals total. Occasionally, blank minus blank. Or maybe 3 blanks add up to a total. But it's a very common structure for a word problem. Here are some more common structure for word problems. Blank times blank equals area, or equals some product. A lot of times it'll be in geometry, and you have to multiply some dimensions to get an area. And filling in those blanks is the details that you have to read from the word problem. And maybe you'll recognize this one. Blank squared plus blank squared equals blank squared. We use this one in the context of, usually, right triangles. Maybe you remember Pythagorean theorem, a squared plus b squared equals c squared. But the lengths written on the triangles are not just going to be numbers. They might be expressions like x plus 3 and x plus 7 and x minus 8 or something for the 3 sides of the right triangle. So we fill in those blanks, work it out. Usually they'll turn into some kind of quadratic. There are some examples. Find 2 consecutive positive even integers whose product is 528. So product means we're multiplying 2 things to get our answer. Blank times blank equals 528. Well, what are we going to fill in those blanks with? Let's talk about consecutive integers, consecutive even integers, consecutive odd integers. You'll see those phrases sometimes in math word problems. Consecutive means just follow on the number line, one after the other, after the other, after the other. Consecutive even means the next even number, the next even number, the next even number. Consecutive odd means go along the number line and just do odd numbers, 3, 5, 7, 9, etc. This time it says consecutive positive even integers. And the way we start these is we make our smallest integer n, and then jump to the next even integer. Well, the next even number is going to be 2 away from the previous even integer. If I'm at 4, I got to jump 2 to get to 6. If I'm at 8, I have to jump 2 to get to 10. So even integers are 2 apart. My next even integer is n plus 2. The next one after that would be n plus 4. The next one after that would be n plus 6. In this problem, we only need 2 of them, so that's all I need to write down. N and n plus 2. These are consecutive positive even integers. Now maybe they're 20 and 22. Maybe they're 26 and 28. Maybe the numbers are 32 and 34. I don't know until I solve the equation. But I know they're even integers that are 2 apart. Blank times blank equals 528. In one of the blanks I put n, in the other blank I put n plus 2. And to solve this, we have all the different choices. Once I distribute the n, we start to realize that this is quadratic. So I now could get everything on one side and factor it. I could do the quadratic formula. I could try to do completing the square. I don't think I would do that. Oh, maybe I would. Now, oh, it's easy to do completing the square, because so what's half of 2? Just 1 and 1 squared. So that's the magic number to put in the blank. All right, I'll do this, but I probably wouldn't expect you guys to do completing the square. You can probably get this by graphing or by factoring or something. This left side factors as n plus 1 quantity squared. The right side is now 529. It's time to do the square root step. Square root of both sides. And just so happens that 529 is 23 squared. So n plus 1 equals plus or minus 23. That's the square root step. Now isolate the letter n, subtract 1 from both sides. And we have -1 plus 23, or -1 minus 23. Now, -1 plus 23 is 22. Could that be my smaller of two consecutive positive even integers? Sure it could. 22 is an even number. The next number up from 22 that's also an even number would be 24. So that number could be a starting point for two consecutive positive integers, positive even integers. Could -24 be a starting number? Well, not if it asked me for consecutive positive even integers. So throw out that -24. That's not a valid starting number. Just use 22 as your starting number and 22 plus 2 as your second number. So our two consecutive integers are 22 and 24. If you multiply them, you will find out that you get 520. Are there other ways to solve this? Sure. Probably guess and check. You might be able to solve it that way. But this illustrates the whole idea of a blank times blank equals a number. Let's see another one that maybe we couldn't solve quite so easily by guess and check. Pythagorean theorem. You got a piece of property shaped like a right triangle. Has one leg that is 20 yards more than twice as long as the first leg. The hypotenuse is 10 yards longer than the second leg. Find the dimensions of the property. So we're going to use blank squared plus blank squared equals blank squared. Right? Very similar to blank plus blank equals total, but this time they're all squared because it's a right triangle. We just have to figure out how to fill in these blanks. Well, read really carefully. One leg, 20 yards more than twice as long as the first leg. Oh, I don't know any of the legs. I don't know any of these measurements, so I guess we could call the first leg, oops, oh, I got to solve this myself. Start writing these in here. Let's just call the first leg X. Because on Pythagorean theorem, we have a leg and a leg on one side of the equation, and a hypotenuse, that's usually the slanted side. Hypotenuse, see if I can spell it right. That's the side across from the right angle. I got one leg, that's first leg, that's going to be X. The other leg is 20 yards more than twice as long as the first leg. So we can write 20 plus 2x. Right? Reading math, you have to pay real close attention to all details. 20 plus 2x. Says the hypotenuse is 10 yards longer than the second leg. So 10 more than what I just wrote. I guess I could write that as 30 plus 2x. Just add 10 to what I already had. 10 yards longer than the second leg. Find the dimensions of the problem. All right, well, this is definitely quadratic. Let's see what it comes out to here. First step will be to FOIL everything out, because it's certainly not in any shape to be using factoring or the quadratic formula or anything like that. We've got to FOIL things out, combine all our like terms, and get it to look more like ax squared plus bx plus c equals 0. Right, that's our goal right there. So let's see, x squared. If I FOIL this one, I'll get 400 plus 40x and 40x, so 80x, plus 4x squared. First, outsides, insides, last. The other side of the equal sign, I got to do first, outsides, insides, last again. First times first, 900. Outside, 60x. Inside, 60x. So plus 120x. And last times last, 4x squared. Right, if you can't do that kind of multiplying in your head, write the thing out twice and then flip. All right, remember I'm trying to get everything on one side of the equal sign. So let's subtract 4x from both sides, 4x squared. Subtract 120x from both sides. Subtract 900 from both sides. So minus 4x squared, minus 120x, and minus 900. And it'll cancel everything on the left side. You have to do it one step at a time, that's okay too. But that should leave us with a 0 on that side of the equal sign. Oh, the minus 4x squared and plus 4x squared, those cancel out. And I guess what we have left here is an x squared. Let me put it in the right order here. The x's are minus 40x and plus 400 and minus 900 is minus 500. All right, now I've got some choices. I can try to factor, I can do the quadratic formula, I can try to graph it, any way that I can to find the solutions of this thing. I'm going to try and factor. But you could try any of those techniques. X times x. Let's see, 500. Come up with some ways to get 500. I could do, 50 times 10. Give me 500. And that would also give me a minus 40 if I do this right. A minus 50x and a plus 10x will equal minus 40x. So all right, I made a good guess right off the bat. 50 times 10, make the 50 a minus and the 10 a plus. So my two solutions of the quadratic are x equals 50 and x equals negative 10. Let's go back to this thing. The piece of property is shaped like a right triangle. What I just found was the first leg. Could the first leg be 50? I suppose. Could the first leg be negative 10? No. Let's throw that one out. Throw it out because it was negative. You can't have a distance that is negative. The length can't be negative. So dimensions of the property. Don't say the dimensions are 50. Well, these are yards. The first leg is 50. The second leg is sitting right here, 20 plus 2x. 20 plus 2 times 50, that'd be 120. And the third leg is 10 more than that. Or not the third leg, the hypotenuse is 10 more than the second leg. So hypotenuse is 130 yards. And there we've got the dimensions of our triangle. I never did actually draw the picture, but if it helps you draw a picture of a triangle. Draw a right triangle and label those sides. X, 20 plus 2x, and 30 plus 2x. It helps you visualize those three sides. There we go, Pythagorean theorem. It all works out to be a quadratic that we have to solve. All right, our last type of problem that we're going to solve with quadratics has to do with what's called projectile motion. So let's watch a little projectile motion here. A little contraption that a friend of mine built. Oh. called a trebuchet, and just built to launch pumpkins into the air. So, so it's kind of fun, but if we actually watch the path of that pumpkin, it follows essentially the path of a parabola. So here's a problem about launching a pumpkin. If a pumpkin is launched from ground level with an initial velocity of 100 feet per second, I think that machine actually launches it from higher than ground level, but that's all right. Suppose we launch it from ground level at 100 feet per second. Its height can be modeled by this quadratic function here. The quadratic formula, S equals negative 16t squared plus 100t. And we're going to answer some questions about this. Find the times when the pumpkin will be 50 feet off the ground. And I say times because what we're going to see is that there's one time when the pumpkin hits 50, but the pumpkin just doesn't keep going up and up and up and up. As we saw, it eventually comes down, splats on the ground. So there's going to be another time when it hits 50, coming back down. We're going to find both of them by solving quadratic. Oh, here's another launch here. Ooh, sailing. Okay, I'm gonna have to. I see. I'm gonna have to go back and solve this myself because it wasn't solved on here. So go back. Here we go. All right. So I'm gonna have to solve this on paper. So find times when the pumpkin will be 50 feet off the ground. Well, 50 is not t. It's not our time. 50 is our height, and height is represented by s. So this is where the 50 is going to go in place of s. I'm going to solve the equation. 50 equals negative 16t squared plus 100t. I've got a quadratic. To solve it, I think I'd rather have everything on one side equal to 0. So I'm going to add 16t squared to both sides. I'm going to subtract 100t from both sides. And I'm going to leave the 50 on the side where it already was. So here's the quadratic I want to solve. I believe I can factor this. Let's see if I can. 16, 150, all those are even numbers. So 2 could go into all of them. That would make these a little bit smaller. 2, and then 8t squared minus 50t plus 25. All right, well, I got started factoring. Now, I suppose I could try to factor 8t squared minus 50t plus 25. Maybe I could do it, but it might not be the most efficient way to do this. Now, if it were easier to factor, maybe I'd continue with the factoring method. But I have better options. I have the quadratic formula. I have calculators. Maybe we should go back to a calculator. We haven't even had this thing on since the very beginning of class. So let's try that. Let's put that into our graphing calculator. Let's see, 16t squared or x squared minus 100x plus 50. I mean, if you want to put the factored version in, you could, but we kind of aborted that method. Said we'll punt that and go right straight to the graphing calculator. And let's see what that graph looks like. We've got some answers. These are not going to be exact answers, but that's okay. Because I think when we're talking about times and an actual word problem, it's okay to have approximated answers here with decimal approximations. So let's see what these are. Second trace find a 0. And let's find this first one. Looks like it's between 0 and 1. So left bound 0, right bound 1. Hit enter, and I get 0.548 seconds. There's our first 0 at 0.548. This next one looks like it's maybe between 5 and 7. Let's try that. Second trace, find a 0. Left bound is 5. Did I get to the left of it? Sure did. And right bound 7. And where is it exactly? 5.701 or 5.702 if we round that. Yeah, I'm glad I didn't try to factor that. Wouldn't have worked. Quadratic formula could have gotten us exact answers for those, but I think this is a good way to express these answers. 0.548 seconds and 5.702 seconds. So choose the tool that's appropriate to solving whatever quadratic you're solving. If the computer really wants an exact answer, then you're going to need to use factoring or quadratic formula. If we're in an application problem, probably okay to have an approximate answer, like these ones. All right, let's see if we got anything else left here. We did the second pumpkin chunking. Oh, here's another one. What goes up must come down. Right? Every time the pumpkin went up, came back down. Well, I want to know when the pumpkin's going to return to the ground. Oh, they didn't give us a height. Like last time, they gave us 50. Or did they give us a height? What would we say is the height of the ground? That should be 0. Oh, so we do have a number to put in here for S. That's going to be 0. So I've got to solve this quadratic. 0 equals negative 16 squared, 16t squared, plus 100t. All right, well, this time I'm going to start by trying to factor again. And let's see if we have to resort to something else. Negative 16t squared and 100t, I think I could factor a negative 4 out of both of those. It's going to be negative 4, and I could also factor a t out of both of those. Look at that. Negative 4t. What's left is 4t plus 25. Oh, it's that first kind of factoring. Remember that? Blank times parentheses. Let's see. Now, I double check. Negative 4t times 4t is negative 16 squared. Negative 4t times 25 is negative, oops, negative 100t. I better fix that. I need a negative times a negative to equal positive. All right, good thing we caught that. Now, our two solutions. This first factor actually gives us a solution. Negative 4t equals 0 at t equals 0. All right, well, yeah, we expected it. It said it was launched from ground level. All right, that part was obvious. Well, the other one, let's solve this little factor. 4t minus 25 equals 0. I got to add 25 and divide by 4. 25 divided by 4, that's, I think, 6 point something. 20. Back to my main screen, second quit. 25 divided by 4, 6.25. So 6.25 seconds. All right, quadratics. We can use them to solve word problems. Once we're in the word problem realm, you can use whatever method or technique of solving seems to fit the problem the best. Whether it be calculator, quadratic formula, factoring, One more thing. On the assignment, you may have problems that say, use completing the square to solve the quadratic. Does the computer know if you used completing the square? No, you're just going to type in an answer. Do I know? No, I don't know. In fact, for most problems where it says use completing the square, I would rather you use the automated completing the square, also known as the quadratic formula. So feel free on those directions. Don't feel locked into one particular method. All right, I think that is all we got for tonight. We made it, 1-4 and 1-5. So thank you guys, and we will see you again on Wednesday night for a little bit more of chapter 1.